Okay, so if you're given a vector, in this case we've got a three-dimensional vector 1, 1, 1, and we want to know, is it in the null space of this 2 by 3 matrix A? Well, how do you check? Let's just go back up to the definition. So what this matrix is a 2 by 3 matrix. So uh, in this case, the null space is going to consist of three-dimensional vectors, right? The number of coordinates of a typical vector in the null space of A is equal to the number of columns of A. So it's got the right number of coordinates, right? This vector 1, 1, 1, it's got 3 coordinates, but how do we know if it actually is in the null space? Well, it's got to satisfy this condition, which means if you multiply the vector on the left by the matrix A, you end up getting the 0 vector. So let's just check that. We just need to check if I take the matrix A, which is this 2 by 3 matrix, and I multiply it by the vector 1, 1, 1. Let's just check, do we get the 0 vector? So this is the product of a 2 by 3 and a 3 by 1. So the result is going to be a 3 by 1. And this is a small enough case where I can just write out the calculation. So we get 1 times 1 plus 0 times 1 plus 1 times 1. And then for the second entry, we're going to have 0 times 1 plus 1 times 1 plus negative 1 times 1. And then if you work out the arithmetic, what you end up getting is 2, 0. So hey, that's not the 0 vector, right? So that tells you this is not the 0 vector, so therefore that the answer is no. This vector 1, 1, 1, let's practice using the mathematical notation. So this vector 1, 1, 1 is not an element of the null space of this matrix A. Okay, so that is our conclusion. All right, so I'm going to leave it as an exercise to you to check that the null space of A is actually a subspace of Rn. Okay, so remember what that involves. You need to check 3 conditions. Let's just scroll back up to the definition of a subspace. You need to show that it contains the 0 vector. That'll be the most straightforward part. Then you need to show it's closed under addition. So you're going to start by assuming that you've got 2 vectors in the null space. Then you're going to show that the sum of those 2 vectors is also in the null space. Then for the third condition, then you're going to show that it's closed under scalar multiplication. So you're going to start by assuming that you've got a vector in the null space, and you've also got a scalar. Then form the scalar product and see if the result is still in the null space. And if you can verify all those 3 conditions, then you'll be done. Okay, so I'll leave it to you to work out the details there. And as always, don't be afraid to seek some help if you get stuck. Okay, but give it a try on your own first. Okay, so that's one subspace that you can generate from just looking at any matrix at all. But there's other subspaces that you can generate in this way as well. The next one we're going to look at is the column space. So if you have a matrix, let's assume it's written as a row of columns. So I've got this matrix A, it's got column 1, column 2, all the way up to column n. So n is the number of columns, but then m is the number of rows. And you can tell that if the matrix A has m rows, that tells you how many entries each of these columns must have. So these columns are actually all m-dimensional vectors. And the column space, so let's actually define it now. The column space of this matrix A is just defined to be the set of all linear combinations you can form from those columns. Or in other words, we have notation for that. It's the span of those columns, right? So the notation for the column space is just COL of A. So that's just short for column. Column space of A is the span of A1, A2, all the way up to AN. And since each of the vectors, or pardon me, each of the columns of A has m entries, they're all m-dimensional vectors, which means that any linear combination of them is also going to be an m-dimensional vector. So it makes sense that this is going to give you a subspace of Rm, not anything else. Okay, so that's another subspace associated with any matrix. There's actually another one too, which we'll talk about in a later section. But there's let's start with an example, just like we did with the previous one. So we've got a vector, and we've got a matrix, and we want to know, is this vector in the column space of this matrix? Well, in this case, based on the definition, what that amounts to checking is what we want to know is this vector 1, 1, 1, is it a linear combination of the 3 columns of the matrix A, because if it is, then that means it's in the span of the columns, right? So let's start by seeing what would that look like if that was true. Is the vector 1, 1, 1, can you write it as a linear combination? So let's make up unknown weights, C1, C2, and C3, to assign to each of these columns, and then let's see if we can make this work. So plus C3, -2, -4, 0. And you'll recognize we've solved problems like this before. This is a vector equation. And if I collapse everything on the right-hand side, I'll have a single vector on the right-hand side and a single vector on the left-hand side. And I can equate each respective coordinate to get, and I'll end up with a system of 3 equations and 3 variables. And its augmented matrix is going to be as follows. Right? This is not a new problem. So this is what you'll get for the augmented matrix. That'll be the constant column, 1, 1, 1. Okay, so what now? Now you just row reduce it, right? You'll need to do the Gauss-Jordan elimination method to row reduce this into reduced row echelon form. And since that's a bit of a distraction from what we're really here to talk about in this section, I'm going to fast forward through those row operations, but be prepared to do some steps here. To start with, you'll want to subtract row 1 from row 3 twice, and then that will clear out the first column. And then once you do that, then you'll want to worry about the second column, and you've already got a leading 1 in the second position, so you can use that to subtract 3 times from row 1 to clear out that 3, and so on, right? You guys are able to do that now, but what you're going to get, and I just want to clarify, this is not obvious. You need to actually do the steps, right? It takes some time to do that, but once you do, this is what you'll end up getting. Okay, you'll end up getting this as the reduced row echelon form. Okay, and then there'll be a row of zeros at the bottom. And then once you get to this point, technically speaking, you already know the answer to the question, because this is the augmented matrix of a consistent linear system. There's no contradictory rows, right? If we had a row of zeros and then a non-zero number here, you'd say, okay, there's no solution. So the answer to this question is no. But in this case, this is just a complete row of zeros. That's no problem. We only have 2 pivot columns, so we're going to have a parameter. So the answer is yes, we can write this vector as a linear combination of the columns of this vector, of this matrix A. But let's go all the way. Let's actually figure out how to do it exactly. So write out the general solution. So let's assign a parameter to C3, and then, for C2, there's a pivot column for C2's column. So to look at the pivot row, write out the equation. You'll get C2 minus 4C3 is equal to 1. Solve that for C2, and then plug in the parameter S for C3. And what you'll end up getting is you get C2 is equal to 1 plus 4S. Right? And then similarly for C3, that's a pivot column. So you write out the equation that corresponds to the pivot row. It's going to be C1 plus 10C3 is equal to negative C2. So solve that for C1, plug in your parameter S for C3 again, and you'll end up getting C1 is equal to negative 2 minus 10S. That's what you'll end up getting for your general solution, where S is just a parameter. Okay, now we could bundle that together into a vector form, but let's not lose track of our goal here. Our goal was not to solve this system and find the general solution and write it in appropriate vector form. Right? Our goal was to answer the question of, is this vector 1, 1, 1 in the column space of this matrix A? And if so, it's kind of automatically implied that if it is the case, we would like to know how. How can that vector be written as a linear combination of the columns? Well, this tells you how to do it. Just choose your parameter S to be whatever you like and use the corresponding values of C1, C2, and C3 as the weights in this equation. So let's take S equal to 0. That's the simplest option. So then that would give you C3 is 0. C1 would be negative 2, and C2 would be just 1. And then we'll plug those values into this equation, and then that's the best way to answer the question. So taking S equal to 0, we get C1 is negative 2, C2 is equal to 1, and C3 is equal to 0. So we can say, okay, the vector 1, 1, 1, it can be written as negative 2 times the first column of A plus 1 times the second column of A. And then you don't necessarily need to include this term, but let's just include it for good measure, plus 0 times the third column of A. And then that now is, by definition of the column space, that is in the column space of A, because the column space of A, remember, it's the set of all linear combinations of the columns of the matrix A. So we were able to show that this vector can be written as a linear combination of the columns, so the answer is yes.